All right. So, so far we've been talking about a simple nonlinear device, which was a diode. We learned how to deal with these diodes in simple circuits, and we saw that there are different models we use depending on the level of accuracy that we want. And despite being the simplest of all nonlinear devices that we deal with, we saw that there's already a bunch of exciting things that we cannot do with linear circuits, that having access to a diode makes them possible, right? So one example was limiting the voltages to the inputs of different sensitive equipment. Another application was, for example, rectification, and there are a lot more. There are a lot more. These are the two main ones that we discussed. However, there are situations that we demand more. We'd like to do more with the input signal. One of the challenges with the diode is that it just turns on and off on its own. It doesn't listen to you, right? It looks at the voltage drop across it or the direction of the current and reacts to that. It doesn't take a command from you. In many cases, you'd like to have a controlled element, something that you can ask it to be on or off, not that it just turns on and off on its own. So it doesn't have that extra input that, let's say, acts on the voltages and currents in a branch based on an input from somewhere else. That's something that you desire a lot. And actually, if you're familiar with a little bit of digital circuitry, that's how all those devices at those in those circuits work, that they take an input, it's 0 or 1, they produce an output that is 0 and 1 depending on the input. But they take a command from you, and 0, 1s are voltages and currents in those circuits. Another thing you cannot do with a diode is that, we talked about the small signal analysis, and we said that in many cases, you're dealing with a large signal that is usually from your DC sources, plus small signal that usually is all the interesting stuff, right? So if you're interested in, let's say, amplifying signals from the antenna, or measuring the signal from a sensor, or monitoring some sort of a change in the environment, this is all the interesting stuff. The DC stuff, the large signal stuff is there in order for you to study the small signals. So that's where all the information is, that's where all the interesting stuff is happening. And diodes give you some capability for processing small signals, but at the end of the story we saw that the small signal diode model is a resistor, which is really not that, that capable, let's put it that way, right? At the end of the story, for example, one of the things that you want to do in many situations in analog electronics is to increase the power of that small signal. It is a small signal, you want to make it a useful signal. It is a signal from a microphone, you want to turn that into a signal that can drive a big speaker, and you can use that to talk to people instead of Twitter, for example. So you need circuit elements that can help you increase the power of a signal. And the small signal model of a diode is a resistor, which is a user of energy. It cannot really add to the energy of your signal. And then there are other cases that you want to do other nonlinear functions. Let's say you want to multiply two signals by each other. And just having a diode in there is not going to make it happen, at least not very easily, not straightforward. So we are searching for a circuit element that gives us a control input so that I can say what I want to do to, let's say, voltage and current in somewhere else in the circuit. And then hopefully also enables me to increase the power of that small signal. What it does in physical terms, in real terms, is that it takes the energy from your DC source, and through those nonlinear transformations adds that energy to your small signal. We will see that we'll separate the DC and small signal operation, or DC and AC operation, like what we did for diodes, for these devices as well. So we do the DC analysis, then we focus on the AC part. But in reality, what happens is that through the nonlinear transfer or the nonlinear characteristics of the device, you take energy from DC domain and put some of it in AC domain at the desired, let's say, frequency. So let's look at an example or let's say an ideal model for something that we would like. It's electronics, so you're dealing with resistors and let's say such here. I'm going to focus on, let's say, slow response of these devices. I'm going to take frequency response or speed out of the equation for now, or out of the concerns for now. Just focus on the characteristics of these devices, and then we'll see that, you know, if speed is a concern, you have to have other better representations. So it's an analog circuit. The input of that analog circuit can be modeled with an input resistor, right? And this is your command. This is your input signal. This is what it takes. Then I'm going to use a current source here, but you know, you can probably come up with an equivalent circuit or an equivalent system for a device that is using a voltage source here. But the reason that I use a current source here becomes apparent or becomes clear very soon. And what happens here is that I have a load on this side, I have a source on this side, and this source controls what happens to the load through this device. So what is in this box sets is the device that I use. This current source, I'm going to use a controlled current source. So when I draw a diamond instead of a circle, it's a controlled source. And this current source takes the voltage drop across Rin, multiplies it by a gain Gm, and produces a current, right? Or maybe I can use capital G here so to stay consistent with your textbook. So if I have an element that does this, take the voltage across a port at its input and converts it into a current, you know, with some gain. That conversion factor Gm is something that we will figure out later. But if it could do that, then the voltage current here will be determined by Vin or Vs, whatever that I have here, right? So I can use that Vs to set the voltage and current at the output. I can use that Vs to make the output current 0. If GMRL, if I look at this circuit, this Vout, this VL, is actually going to be GM Vin RL. You can do the quick calculation for yourself to convince yourself this is the output. If that GMRL is larger than 1, which hopefully I can do that, then I actually have some gain. The output voltage can be larger than the input voltage. And so on. So I'm looking for a device that can do this for me. As you can see here, I have 4 terminals, but I can maybe share the ground between the input and output here. And therefore, I only need 3 terminals, one here, and one here. So I'm looking for a device that has 3 terminals, and the relationship between 2 of the terminals, voltage current relationship between 2 of those terminals, is controlled by the relationship between another 2. So these 2 are going to be my output. Let me use a different color. So this terminal is going to be my output. There's a current and a voltage there, and this is my input. So I want to have an input and an output. To save on the number of pins, I'm sharing the ground connection between the input and output. So 3-terminal device that can do this. And let's go and search for such a device. Now, the first thing I note here is that, you know, making a resistor is not a big deal. But we haven't seen a current source yet. Or maybe we haven't, right? So how do you make a current source? So this is the part that we haven't done yet, right? You know how to deal with a resistor, you know how to deal with capacitors and inductors, and you know, physically you know how to make all of those resistors a piece of any conducting material. Capacitor is 2 electrodes separated by some gap between them, and an inductor is a winding, right? So we know how to make them. We also know how to make a diode. We take a semiconductor, we dope one side of the semiconductor with, let's say, N dopants and the other side with P dopants, make sure they have a proper interface between them, and you get a PN junction that behaves like a diode. And it has that exponential current voltage relationship that we find very interesting. How do we make a current source? And I guess based on what you know so far and all these components that I mentioned to you, you may be able to come up with a device that can act as a current source. So what is a current source? A current source is a device that you can change the voltage across it, but the current through it will be constant. So whatever you set the current, it will be that regardless of the voltage that you apply to it. It is similar to a voltage source. We have seen voltage sources, and actually we know how to make voltage sources, right? So it produces a fixed voltage regardless of the current that you draw from it. What is a good voltage source? You know, most batteries can be considered as good voltage sources, and we can make them electronically as well. But we haven't seen a current source, and at least not one that we can put on a circuit easily and use it. So I want to ask you to pause for a moment and go through your memory and search for a device that can act as a current source. You already know about it. I'm going to give you the answer in a second. But find that device that at least behaves like a current source. You know, the current through it is independent of the voltage drop across it, at least over a portion of its operating region. And then we come back and continue. Okay. So hopefully you may have come up with different ideas, but I'm going to give you one device that can act as a current source. A reverse bias diode. So if this V is larger than 0, a reverse bias diode, what is the current through it? It's just IS. So we saw that, right? And assuming that you don't hit the breakdown region, a reverse bias diode actually behaves as a current source. The voltage doesn't affect that, as long as you keep it reverse biased, right? So when you look at the input-output relationship, ID, VD, as long as you stay to the left of this VD 0 volt, you have a current source, right? So if you put your device, if you bias it here, or if you bias it here, for small changes around that point, you effectively have a current source. The current doesn't change. What is the problem here? The problem is that this IS is really small, right? So we saw that for typical diodes, you're talking about a microamp of IS for a large diode, for, you know, typical diodes that you use in the lab or you buy from electronic shops. You're talking about nanoamps or picoamps for the IS, for the saturation current of the diode, which is too small. For more practical applications, you need currents on the order of milliamps or higher in order to do some meaningful electronic work with them, right? So you need milliamps of current through an LED to make it bright enough. You need tens of milliamps through a small speaker to be able to hear that sound. You need probably amps of current through a heater to produce a noticeable amount of heat. So picoamps and nanoamps and femtoamps, yeah, you have a current source, but the value is not really that interesting. It's just too small for being useful. Now, what I can do, or what the engineers or scientists did, is that they said, okay, so let's play a trick here. We designed this diode that has a really large reverse current through it. And in order to do that, what they did is that they came up with this structure. Instead of making a diode that is just P and N, they created a sandwich of these materials where you have an N layer, a P layer in between, and then an N layer at the output. You can have an alternative arrangement where you have P, N, and P. Let's start with this. We'll talk about that arrangement later. So you put two of these together. Well, from the discussions that we had before, we know that This gives you one diode in this direction, and this gives you one diode in this direction. I make a contact to each one of these regions, right? And I'm going to give them names for now. We'll come back and see why we call those pins the way that we do. But I'm going to call this one an emitter. I'm going to call this a base, and this one a collector. Now, what I want is a current source. So let me make this diode reverse bias. So base, basically, the two ends of these two diodes are connected to each other. So this is base, collector, and emitter. So what I want is a current source. So let me reverse bias base collector diode. If I reverse bias this diode, the reverse current through it is going to be fixed. So let's just call it IC. It's going to be fixed. A reverse bias diode behaves like a current source as we just discussed. But the current was too small. So what I do is that I forward bias this second diode. By forward biasing this second diode, so this, so BE forward or on, and BC reverse. So what I'm going to do for the rest of this course, for most situations, I'm just going to call it on and off. It's just easier, faster. When I say diode is on, I mean it is forward biased. When I say diode is off, I mean it is reverse biased. So if BC is reverse biased so that I get my control, my current source, and B is forward biased, let's see what happens here in this device. So in an N region, you have a lot of electrons that can move about. And in a P region, you have a lot of holes that are your charge carriers, and again, electrons here. We notice that we have two junctions here, so basically a depletion region will exist here between these two sides, and another depletion region here. And we said we call these depletion regions because they're depleted of charge carriers. The electrons that we had on the N side have diffused into the P side. I have a bunch of positive fixed ions here, and the same amount of negative ions on the other side of the junction. And then over here I have the same situation, a depletion region that separates the P and N sides from me. And but this depletion region is a bit wider because I've reverse biased this section. And if things are under equilibrium, let's focus on the base collector diode here. If this is reverse biased, I know that there's not really that many electrons that can jump over that depletion region. So if I want to maybe elaborate a bit here, once I put a reverse bias here, the depletion region becomes a bit wider, right? And by becoming wider, it means that it just made it harder for the electrons on the N side to jump to the P side, or for the holes on the P side to jump to the N side. So that gives us the fixed current, right? So that's what I wanted. Now, because now I have this large electric field inside here, what happens on the side is that if for whatever reason, so you have an electric field that points in this direction, right? If for whatever reason I have a hole here, it will be thrown into the base region. On the other hand, if I have an electron here, it will be thrown to the collector region, right? So if you produce an electron or hole very close to that depletion region, they will see that field and they will be thrown to the other side of the region. So if I come up with a way to produce a lot of electrons near that border, I can make that reverse current much larger than what it is. It is still a reverse current. It is still independent of the base collector voltage, but I have control over it, hopefully, through other means. How do I do that? I do that by forward biasing this second junction here. By forward biasing this second junction here, what I do is that I make that depletion region a little bit narrower. I make it easier for the electrons on the N side and the holes on the P side to jump to the other side. So as soon as I forward bias this, I expect a lot of these electrons to jump to the P side and some of these holes to jump to the P side, to the N side. Good. So I'm producing a lot of electrons here in the base region. Make my base as narrow as possible so that the electron that comes here will have a chance to get to the edge of this depletion region before it recombines with holes. If I make my base region narrow enough, That will happen to most of the electrons that are thrown into the base region from emitter, and they will see the collector depletion region, and they will basically hop to here and then hop to here, right? And therefore, but that field that I have across the depletion region here, the voltage, or the other way, in other words, the voltage that I put on the collector doesn't affect the flow of those electrons. I produce these electrons here at the emitter region, I throw them into the base region. So the base emitter voltage, which determines the width of that depletion region, determines how many electrons I put in base, and then everything that I put in base, hopefully, will get to the collector. I know that's not true. Some of the electrons that show up in base, because I have a lot of holes here, will recombine fit with those holes, and I lose some of the electrons from the left side as they travel to the right side. Now I can see why I gave those names for those three regions. Emitter is where I produce these charge carriers and I inject them into the base. The charge carriers are emitted from the base side. Collector is where all those charge carriers that came from the emitter are collected and then thrown out to the other side of this junction and basically passed on to the external circuit. Base is where basically I have it to keep everything in balance. I will have currents for all these three regions, right? And we'll talk about that. But this is the function, this is the structure of an NPN device, an NPN transistor, and how it works. I have a base collector device diode that is reverse biased. I have a base emitter diode that is forward biased. If I play with the current of that base emitter diode, if I bias it a bit more strongly, if I pass, let's say put a larger voltage on it so that I get more currents over there, all of that current will actually go and show up in the collector circuit where I have a current source. Now, in terms of a circuit symbol, if I look at that, a transistor is shown like this. A BJT, bipolar junction transistor. So why do we call it a bipolar junction? Well, because I have these two junctions here. This is the symbol for a BJT transistor, NPN BJT. You know, we have two cases here. We have two ways of making this device. Another one is to start with a P, put an N between, and have another P layer for the collector. Let's focus on this device. So this is an NPN bipolar junction transistor. Okay? And internally, I know inside this device what I have is a diode between the base region. So the base is the P here, N is on top, N is at the bottom. I know I have a diode in this direction between the base and collector region, and I have a diode in this direction between the base and emitter region. So this is collector, emitter, and base. Like diodes, I choose and I set the voltage and current directions here for this device. So for an NPN BJT, IC goes into the collector terminal, IE comes out of the emitter terminal, and IB goes into the base terminal. So IB is like this. IC goes in, IE comes out. Okay? So in here, I will have the same thing. IB goes in, IC goes in, IE comes out. Okay? And if that's the case from KCL, I know that IE should be IB plus IC. Regardless of what is happening inside that device, KCL holds. If I choose those directions for the currents, that's what I should have for the sum of these currents. Okay. Now, I have two diodes. I have four possible situations. Let's write them down. I have the BE diode, and I have the BC diode. Okay? So there are 4 possible situations here. I can have a BE diode that is on and a BC diode that is off. This is the situation that we just talked about. Okay, so one situation is that the base emitter diode is forward biased, base collector is reverse or on and off. Another situation is that both of them are on. And I have another one where both of them are off. And then the 4th possibility here, depending on the circuit that you put around this device, is that the base emitter is off and the base collector is on. All right. So 4 possible situations. I can have nothing more. Either both of them are off, both of them are on, or one is on, one is off. Right. So this arrangement is going to determine the operating region for my transistor. If the base emitter diode is on and the base collector diode is off, I say the device is in active region. And we'll see the reason for these namings before. If the base collector diode is off and the base emitter diode is also off, what happens here is that I have these 2 junctions side by side, but I do not produce any, let's say, electrons from the emitter side so that the collector side can basically collect them and put them out. I do not inject anything into the base. I have 2 off diodes. The device will be in cutoff region, or simply we call it cut off. Both diodes are off, 2 open circuits, nothing happens. Nothing interesting at least happens. If both diodes are on, what happens is that I have a diode on the base emitter side that is injecting a lot of electrons into the base. I have a diode on the base collector side that is also injecting a lot of electrons into the base. So it is the opposite of what I had for the active region. Both of them are on, both of them are injecting current into the base. Some of that will be used inside the base during recombination, but a lot of it will show up in the base as an extra current. We call this the saturation region. And then we have this last item here where the BE diode is off and BC diode is on. It's the opposite of what we said at the beginning, where we had a basically controlled current on the collector side and an emitter on the BE side. It's going to be the opposite, so we call it a reverse active. And, based on what we just said so far, it should be basically the same as active, right? I just swapped the 2 pins. But what happens in reality is that when you make these devices, you don't have the same doping levels on the emitter and the collector side. You actually have higher doping on the emitter side. So it's not a symmetric device. Emitter has a higher level of doping than the collector. For that reason, for example, what happens is that VBE on is going to be larger than VBC on, because emitter is made a bit differently. So for the same current, let's say 1 milliamp, if you push it through base emitter junction or base collector junction, you get a larger voltage drop on the BE side than the BC side. It's not a symmetric device. And for that reason, reverse active, yes, the device still behaves as a transistor in active region, but like a bad transistor. You lose a lot of those good things that you wanted by making this sandwich structure. You lose a lot of those benefits right there. So while these 3 other regions, active, saturation, and cutoff, have their applications, reverse active doesn't have an application. It may happen by chance, because of poor design or neglecting something in your circuit, or maybe you just put the transistor in your circuit with, let's say, in the wrong orientation. It can happen. Your circuit may still work, but you've paid for a device that you're not basically using to its full potential. It's going to be a bad transistor. So we'll see one of the parameters that define a good transistor are the device can still act like a transistor in active region, but as a poor one, not definitely like one that you paid for. So this is an NPN transistor, right? And then if I want to maybe add one more thing here. So this is KCl that always holds regardless of the voltages that you apply to this device. So internally, again, you can think about it like a sandwich of 3 layers, N, P, and I'm going to write N plus. So the emitter has a higher level of doping than base. So this is my base, this is my collector, and here is the emitter. Okay, that's my NPN device. I'm going to focus on NPN. PNP is going to be very, very similar. It's very essentially an alternative arrangement for these diodes. And the 3 operating regions for a PNP, I just mentioned that quickly, are going to follow this same table here. So if the BE diode in a PNP is forward biased and BC is reverse, that's active, and so on and so forth. But I'll come back to PNP quickly at the end of this discussion. Okay. Now, let's look at the response of that arrangement of diodes or junctions to external stimuli. And in this case, for us, the stimuli is voltage and currents, right? So I'm going to use voltage sources here. I'm going to keep the device in active region. The cutoff region is the easiest of all. You have 2 diodes, you replace them that are both off, you replace them with 2 open circuits, and you'll be done. The saturation region, again, it's a bit more involved, but still, 2 diodes that are on, and you can go and solve the circuit easily. The active region is the new one, the area that we probably need a little bit more attention. And this is where we usually use the device in any way, right? So we usually bias the transistor in its active region in analog electronics. And I'm going to focus more on the active region for now. We come back to that other regions later on. So I remember that I have a diode between base and emitter, as shown on that graph, common base, and then 2 N regions. One is used at the collector terminal, one at the emitter terminal. So we saw that KCl imposes this on us. IE is IB plus IC for the direction of currents that is shown in this circuit. Now, we said that you have a diode at the base emitter region. It is forward biased. So you expect IE to be proportional, based on what we learned before, to e to the VBE over VT. But what happened to that N? It's a diode, so what happened to that N? Well, when we make these transistors, they behave actually very much, each one of those junctions behave very much like an ideal diode with ideal characteristics. So that N is very close to 1 for a BJT. So there is that N is there, but N is 1. So we expect IE to be proportional to VBE over VT, the exponential of that term, just because it's a diode. So some IS times EVBE over ET. But we said the current that comes from the emitter shows up in the base, and most of those charge carriers are absorbed or thrown to the collector region. So we expect IC to also be proportional to VBE over VT, right? Remember, the base collector diode was reverse biased. It was collecting all those electrons that showed up in the base region close to its depletion region. Whatever that reached there, it would just throw it to the other side. So I expect, if that a portion of those electrons reach the edge of the depletion region, I expect the current that I see at the collector terminal to also be proportional to VBE over VT. Now for this one, what I do is that I write it like this. IC is some saturation current times e to the VBE over VT. And then you have that -1 if you want to be super precise. But again, we saw that it's really not that big of a deal. That 1 as soon as VBE is a little bit larger than a few times VT, that one goes away. But this is the current voltage relationship for the collector current and base emitter voltage, right? Base emitter voltage is this. This is VBE. And okay, so if you want to write it this is VBC, and then this is VCE. So when I say VBC, I mean VB minus VC with respect to ground. Or when I say VBE, I mean VB minus VE. The voltage drop across that terminal on the two sides of that diode. Okay, so we have that relationship for the collector current. We see that it should be, basically IE should be a multiple of that, probably a bit larger, right? Because a portion of the current from the emitter shows up in the collector. And then IB will be the difference between these two. Now, what you can see is that, so therefore, because of these two and the first relationship that you have here, IB also is going to be proportional to EVBE over VT. All those three currents will be proportional to E to the power of VBE over VT. Now what happens from device physics, or what we can choose to do is that we can say IC, we choose it to be a multiple of IB. So IC is beta times IB. Remember, all of these are linearly proportional to EVB over VT, so each one of them is a multiple of the other. So the relationship between IC and IB we show through here. The relationship, for example, for IC and IE, I can, for example, do it like this. IC is alpha times IE, or IC is beta times IB, right? And these are the equations, once you accept the fact that, let's say, IC is proportional to VB over VT, the rest of it just follows, okay? Now, here is the interesting bit. If you make your transistor properly, if that base region is narrow enough, beta here tends to be much, much, much bigger than 1. Typical values are between 100 to 300 for beta, right? Interesting. So a small base current can actually give you a very large collector current. You can play with that. And then for here, what you will see is that you will notice that alpha, if beta is that large, plug this into this equation, do the math, you will see that alpha is equal to beta over beta plus 1, and therefore very close to 1. What does that mean? It means that the collector and emitter voltage currents are more or less the same. The collector current is always a bit smaller because alpha is always less than 1. But if beta is 100, the fraction is 100 over 101. It's 0.99, right? They are very, very close to each other practically. So I would want to maybe change the low end in this range. If you're dealing with power transistors, beta can be as low as 50 or maybe even 20. But it is still much bigger than 1 for most practical applications. And then beta, if alpha is 50, beta is still 0.95 or something. So there are two equations that I want you to remember from this bunch. I'm going to rewrite them here to emphasize. So this is VBE, this is VBC, which we keep such that the base collector diode is reverse biased. At the very beginning, I suggest you do this all the time for the first maybe 10 problems that you solve. I draw these little diodes here to keep myself, reminding myself that what should be the orientation of these diodes and then their biasing. And the collector current and all the currents have predetermined directions. So you do not choose IB to come out of the base of an NPN transistor. This is NPN. Okay? So two equations I'd like you to remember. First one is that IC is beta IB. And by extension, alpha IE. So I'm going to count this as one equation because alpha and beta are related. And then the second equation is IC is IS e to the VBE over VT. Okay? So you have a device that has 3 terminals. You have 2 equations that describe the operation of this device. If you put this device in a circuit, you have to be able to solve that circuit, because you get 2 equations for this device, and then depending on what you have around it, you combine it with KVLs and KCLs, and hopefully that will be all you need. One major note here is that this is for active region. We'll talk about the other regions later, but this is the important one. This is where we want to keep the device. This is where a lot of those interesting things happen. So this is an NPN BJT in active region. Okay, so the foundational equations are these two. IC and IB and IE are linearly proportional to each other. IC and IB, there is a beta factor between them that is usually much, much bigger than 1. And IC is exponentially proportional to VBE over VT. Right away you can see that you have your controlled source, right? So if I want to come up with a circuit model for this device, I can make it like this. I can have a diode between the base and emitter regions, a controlled current source between the base and collector regions. So this is the base. I use emitter as the common node between the input and output. So I can come up with an alternative model, right? So where I have a, maybe I'll draw that later. So this is one model that I can have. So this IC is beta IB or IS times e to the VBE over VT. So I look at here, I look at the left side of this circuit, the left side of this device, I see whether I have IB or VBE, whichever I have, I can find IC based on that. So this is IC. And remember, IE comes out, right? So I look at the left side of this circuit. If I have IB, I say IC is beta IB. If I have VBE, I calculate VBE IC from that. So this is one model that I can come up with. I could also come up with an alternative model where I have my current source here, base is connected between the two, and then I have a diode here. This is more realistic. Remember that I had those two diodes, right? So one junction here, one junction here. This is the base terminal, collector terminal, emitter terminal, and this is VBE, and of course IE goes out, IB goes in, IC goes in, and this is therefore VBC is going to be the voltage here. Okay, this is actually easier to come across, right? So if you take that device, that symbol, you can see that this is what is happening inside it. Now, why do I prefer this model at the top? It's usually because emitter is usually my reference. I measure my voltages with reference to emitter. So VBE or VCE, emitter is connected to my ground or is very close to my ground. And for that reason, I'd rather like to use the model on the top. And the other reason that I like it is that if you look at it, you have the right side of the circuit that is controlled by the left side of this circuit. It's as if I have separated my input and output here. This other model doesn't do that. This one at the bottom, everything is mixed up and together all the time. So for that reason, you see the bottom model in your book, and from time to time, I think if you check other sources, but when it comes to solving circuits, the one at the top is a little bit easier to do things with, right? To separate input and output with. And that's the one that I will be using all the time. And then when we talk about the small signal model of the transistor, we'll see that it's going to look like very much like the top one, and that's where we replace some of these elements with other ones, but it looks, topology looks the same. Now, in terms of the IV characteristics for this device, let's look at one situation here. So this is my transistor again VBE and VBC. And what I'm doing here is that I'm going to apply a set of voltages from outside to this device and measure the currents and see what happens, right? So between the base and emitter, I put a voltage source here, whose value is VBE, and between emitter and collector, I put another voltage source here. So this is VCE. Okay? The goal is to keep the device in the region that you desire. So active, cutoff, saturation, whichever, whatever, right? So if I want to have active region, I, for example, need to make VBC larger than, VBC, the collector voltage has to be larger than the base voltage. So VBC should be negative, VBE should be larger than VD on, and so on and so forth. So this is VBE, the source. I use the name of the source to be the same as the name of the junction, just to avoid confusion, right? So two voltage sources, and let me do one more thing. I'm going to take ground as my common node, so it is emitter as my common node, and then I notice that, again, I'm going to stick to the convention. IB goes in, IC goes in, IE comes out. Okay? So I'm just concerned a bit that these things may not be, these notations, some of it may not be visible. So please give me feedback if you cannot see any of these drawings. So I have two sources, and I'm going to change these two and see what happens to the currents. I want to figure out the input-output characteristic curve. Input in this case is what happens in base emitter side. Output is what happens on the collector side. So first thing I'll do is that I keep the device in active region. I start changing VBE. And I want to see what happens to IC. Okay? Well, that's easy. As long as my device is in active region, meaning that the base emitter is on, what I expect to see is an exponential relationship. Remember that IC was IS e to the VBE over VT, right? So give it a little bit of VCE, just a tiny bit, I don't know, enough to keep it reverse biased, maybe 5 volts, so apply 5 volts here, and keep changing this VBE from, let's say, 0 to 1. Remember that the diode turns on at around 0.6, 0.7 volts, and all of a sudden conducts a lot of current, so your VBE range is limited, and just so that the base collector remains reverse biased at all times, if you put 5 volts up there, that base collector diode is going to be reverse biased all the time. This is base collector, this is base emitter, right? And then you can play with VBE to see what happens. And obviously, this is what you expect to see. The collector current is exponentially proportional to VBE. Not that interesting, right? Now, so let's do one more thing. Let's do one more experiment where I keep VBE constant and change VCE. So let's say VBE is large enough so that I have a noticeable current in my collector, let's say 0.5, 0.6 volts, not over here, but let's just say VBE, I choose it to be here, okay? I apply that VBE and then change VCE, the collector emitter voltage, and then I notice that, well, for a given VBE, I get a constant output. This is what I wanted. This is actually what I've been after. I get a current source. If I change VCE, it's as if I have a current source between these two terminals, which is what I wanted, right? and which is actually what is shown in the model here, the current source. So for a given VBE, I get a constant current. Change to a different VBE, slightly larger value, let's say VBE1 and VBE2, and you get a different value. Right? And it is constant. Once you set that current by establishing your VBE, the output current at collector is constant. And it is good for all large values of VCE. Something funny happens when VCE becomes too small. You know, as you reduce this VCE, there is a chance that at some point you may forward bias that diode. So let's say you put 0.7 volts here at the base, and you try to reduce VCE. At some point you may have, let's say, 0.2 volts here or 0.1 volt here. So now the base collector diode is actually forward biased by 0.5, 0.6 volts. And as soon as that happens, your IC will start to drop. So for small VCEs, this is what you're going to see. The current source that you had before, you don't have it anymore. Remember that to have that current source, the diode has to be reverse biased. You start to slowly forward bias it, so you lose the nice current source that you had before. This is the saturation region that we mentioned in that table in the above. Beyond that, you have active region, right? So as long as you have a measurable current through the collector and emitter, and you keep the collector, base collector reverse biased, you have a device in active region. But if you drop the collector emitter voltage, if you slowly forward bias the base collector junction, you get into saturation region. And then if you want to talk about the cutoff region, it's over here. You know, when your base emitter junction has not turned on, or it's, you know, even worse, it's reverse biased, and your base collector junction is also reverse biased. So that's where you will be in cutoff region. So this is cutoff. Your IC will be 0, your IB and IE will also be almost 0. And it's not needed, or it's not used in typical electronic circuits. However, in switching circuits, you love these two regions, I mean saturation and cutoff. In switching regions, well, you put VBE close to 0, you turn off VBE, you turn off that junction, all of a sudden the connection between the collector and emitter is open, you have an open circuit there, you have an open switch. Or you put such a large VBE over there and design such a VCE over there that the device goes into saturation region, and once it is in saturation region, VCE will be very small, you know, 0.1 volts or 0.2 volts, something in that range. And it's as if you have closed the two sides. It looks like a closed switch, right? So if you want to have a relay that opens and closes, this could be the answer. And this is how you make digital circuits that have two states, 0 or 1, on or off. In analog electronics, we usually are somewhere in between. We don't want the device to be full in saturation or in cutoff. We keep it in active region. That's where we have all sorts of interesting phenomena happening. We have a lot of control over the device behavior. But digital electronics is easy. It's just going from off to on, off to saturation, and back. In analog electronics, I would say 98-99% of the cases, you keep the device in active region. You still use cutoff and saturation from time to time for doing some special functions, but in the vast majority of the cases, your device is in active region. And that is going to be our introduction to BJTs. That's the lecture here. Let me solve one example for you here. We go through one example from your textbook. So it says we have this circuit. So the base and collector, the base is connected to a current source whose value is 10 microamps. I have biased this transistor using a power supply voltage of 5 volts. Notice the notation that I'm using. I do not create the loops and rails anymore. I just show that sign and label is 5 volts. This RC is 3 kilo ohms. And the NPN device here, we are told that has these characteristics. For this NPN device, IS is 1 femtoamp and beta is 100. Okay? Now the question is, what are okay? So this is your transistor in a simple circuit. The question is, what are VBE and VCE in this circuit? And what I'm going to notice here is that this is one of my early examples. I'm going to draw my transistors here, keep myself mindful of the fact that there are 2 junctions. I label the voltages and currents. And I put the directions of the currents on the graph. So this is collector, emitter, base, right? So I do that to keep myself, to remind myself of how things are here. Now, the second thing I do is I go and check my formulas. I see that IC is IS e to the VBE over VT. And because I know IC and IS and VT is room temperature 25 millivolts, right? So let's just make that assumption explicit here. I can right away see that VBE is, I need my calculator. Oh, sorry, I don't know IC yet. Okay, so I don't know IC yet, no problem. I know beta. Beta is 100, IC is equal to IB, and IB is 10 microamps. With the direction of current here, I can see that VBE, the base emitter junction can be forward biased. Basically, the current source here will accommodate any voltage that is needed here at the base to make sure that the base emitter junction is forward biased. So I will have 0.7, 0.6 volts at the base, and hopefully base collector will be reverse biased. I don't know at this point. I need to verify it later on. But let's assume this device is in active region. Assume active. And with that, I can actually see that IC is then 1 milliamp. It's 100 times 10 micron. And from here, and this equation, I can see that VBE is 0.691 volts. So VBE done. VCE, I need to do a little bit of calculation. So VCE is the voltage from here to ground. That's VCE. And the way to do that calculation, well, I know the emitter voltage is 0. The collector voltage, there is a current source at the bottom of that node. And that current source, I really cannot say anything about the voltage across a current source, but I can calculate the voltage at the top node if I go down from here. So VC, I can see that is VCC minus IC RC. And IC, I have 1 milliamp for it, RC is 3 kilo ohms, VCC is 5, so I have everything I need to. So minus 1 milliamp times 3 kilo ohms, and that's 2 volts. And once that I have that, because VE is ground, therefore VCE is VC minus VE, and that's 2 minus 0, and that's 2 volts. So done. Okay, so I solved both. I have the values that I needed. I'm not done, actually. I need to make sure that my device is in active region. So I'm not going to do that now, but go in, between this lecture and the next one, do the math, make sure that you are convinced that the device is in active region. Go back to the table, figure out or remind yourself what the conditions for active region were, and come back and see if they apply here. And with that, I think we're going to end this part of the lecture. What we do in the next lecture is that we'll go and see how we can solve transistor circuits under DC conditions, and at some point we'll go and see what is the difference between an NPN and PNP transistor in these kind of situations.